Okay, so this is the BDL compact vessel capstone project. So right here is our polystat heat bath. This basically cranks the water temperature up using a internal heating element, and it's also got a pump within it to basically send to our pump over here. Additionally, there is also a sensor below there for if the water level gets too low, it'll trigger an alarm and start beeping. It's very hard to see, but there's a red line that I marked which indicates the level at which it triggers. So the fluid comes out through here and then goes to this little T section, and it either goes to this bypass, which goes right here, or goes to the pump. Now, right now, the bypass is open. However, if I want to increase the pressure, then I can basically turn the stopcock. So right now, it's reading about 81, and that's in millimeters of mercury. So I close off that section. What? Oh. And the calibration's a little bit off, but as you can see, there's an alarm going off. That is meant to basically warn the user in case there is too much pressure in the system. And right over here is our peristaltic pump, which has a stepper motor on the top, which is controlled by a driver and a controller that is within our faceplate over here. I'll take a second to talk about the faceplate. This little knob is a potentiometer used to increase or decrease the stroke rate of the peristaltic pump. It's moving quite a bit right now, and the pressure is about 50. But if I turn this up a bit, then you can see that I'm at about 90. And this is an instantaneous pressure. The bottom is the maximum temperature that it has read in the past several minutes. These buttons all across here are our calibration values. So the button right here calibrates it takes the high voltage associated with the pressure value, so in this case 200, and this one takes the low value, which in this case is 50 millimeters of mercury. After you press the second button, it determines the slope value, or it determines the second value, and the program continuously determines the slope value, and that's how you get the calibration curve for the system. And then this side basically does the same thing, except for the second pressure transducer. So this pressure transducer is controlled by this set of buttons over here, and the pressure transducer that normally goes right over here, which is connected to this sphygomanometer, is controlled by these buttons right here. This button right here basically reverses, or this button right here completely stops the pump. As you can see, it's going back on now. And this button right here reverses the direction of the pump. So that is all the buttons on the faceplate design and what they do. The driver and the controller are both within the electronics housing, and same thing with the Arduino. Sensors for the pressure transducers and the alarm notifications. So that covers the pressure transducers. Here is our manifold. We made this to basically optimize our system so that we could incorporate different models at once. So for instance, all of the middle stopcocks on this side of the manifold are going to be the ones that you control when you are operating the pump, and you would not operate these ones when the pump is not being operated. So if there was a leak somewhere over here, I would basically close this off. A little bit of pressure shot up, but if I wanted to prevent any sort of leaks happening right over here, then I would just close this. And now that I've demonstrated that, I have flow returning back there. So we also have these connectors right over here, which basically you can change shapes for models with differences in diameter.
Say that again. Just say it all over again.
These tubing types, so basically these connectors allow the user to change different tubing types based on the diameter of the interior of the model, or of the inlets. And then right over here is our bypass. This is always on regardless, but it basically allows the fluid to relieve. That way, so there's not too much pressure buildup happening within the vessels and they don't burst. So basically, the flow that is being added by the pump goes through the bypass over here, and then it comes back to the filter. Bringing us to the filter, we have a stopcock over here and a stopcock over here, and we also have two stopcocks over there. You would basically seal both of these. I'm not going to do it right now because the pump is currently running. Actually, psych, I will. But you can basically cut these, cut the flow of these off, and then you can cut the flow of these ones off. And then you can take apart the filter and say you are done with the cleaning process. In a less messy fashion, you can easily disconnect the filter and then reapply it for your next model. But yeah, and then this filter basically helps separate the support material particles that are pretty large, that have not been dissolved by the hot water, while this filter helps separate the more dissolved fluid part, or the more this pump right over, this filter right over here basically helps filter out the dissolved particles of support material after they have been sitting in the water. That way, so they can safely return back to the fluid reservoir after it is done operating.